Good morning. My name is Stephen Smith, and I am the IonFlux Technical Director for Fluxion Biosciences. I'd like to thank you for taking time today to learn a bit about the IonFlux automated patch clamp system and their use in biophysical and pharmacological characterization of the voltage-gated sodium channels. Just a few process details before we get started. There's a WebEx Q&A panel located on the right for submitting questions during the course of the presentation. We will get to as many questions as possible after the formal presentation, which will run approximately 30 minutes. If we don't get to all of the questions, we will respond via email. So please feel free to ask questions during the course of the presentation. In today's webinar, I will give a brief overview of the IonFlux systems and the software interface. Since we have two recording modalities, the single cell configuration and the ensemble recording configuration, I will highlight the differences between these modes. In terms of the instrumentation, it is important to note that the only difference when using the system is the choice of plate type for the experiment. I will then highlight some of the data we have collected characterizing the biophysical properties of a few members of the voltage-gated sodium channel family, and finally highlight some of the pharmacological characterization. Voltage-gated sodium channels, or NAVs, are found in most excitable cells, such as neurons and muscle cells. They're responsible for the fast upstroke in the action potential. After opening, the channels rapidly inactivate. Shown in the upper right is a cartoon of the membrane topology of the channel-forming alpha subunit. There are 4 domains, each with 6 transmembrane spanning segments. The pore is formed by the 5th and 6th membrane segment from each of the 4 domains with the signature reentrant pore loop. The 4th membrane segment has a number of charged residues and functions as the voltage sensor. The intracellular loops have sites for phosphorylation, which leads to modification of function, and the loop between domain 3 and domain 4 is the inactivation gate. Not shown are the beta subunits, which can modify function, but are thought to be more important for trafficking and localization. There are 9 NAVs. NAV1-4 and NAV1-5 are found mostly in muscle, skeletal, and cardiac muscle, respectively. And the others are found mostly in neurons of the peripheral and central nervous system. The NAVs are hotly pursued targets in drug discovery efforts. They have long been used as antiarrhythmics, for instance, drugs like flecainide and propafenone. NAV1-7, 1-8, and 1-9 are being pursued for the treatment of pain. With genetic mutations, both gain of function, which causes a hypersensitivity, and loss of function, which leads to an indifference to pain, indicating that blocking the NAV1.7 should be useful in treatment of pain. And Pfizer now has a NAV1.7 specific compounds in clinical trials. Also, the NAVs are being pursued for seizure, epilepsy, bipolar disorder, myotonia, and migraine. A bit of background on the IonFlux system. The IonFlux system was developed to address needs both within the pharmaceutical research community as well as the academic research environment. In large pharma, the problem is that functional ion channel screening is difficult and expensive. In academia, manual patch is training intensive and low throughput. The IonFlux systems are benchtop instruments that operate like a plate reader. The systems are modular and expandable. We have 2 versions of the IonFlux. The IonFlux 16, which makes 16 simultaneous recordings, and the IonFlux HT, which makes 64 simultaneous recordings. With the IonFlux 16 priced at about the price of a manual patch rig, the systems are very affordable. The unique microfluidic well plate means that multiple experiments are performed in parallel with exact synchrony across the plate. Taking a closer look at the well plate microfluidics, shown on this slide is an IonFlux HT with an SBS standard 384 well plate ready to load into the instrument. By using an SBS standard footprint, the IonFlux 16 and IonFlux HT plates are compatible with standard liquid handling robotic systems. Shown on the right is the bottom of an IonFlux HT plate, showing the well plate integrated microfluidic network, which consists of experimental patterns of interconnected wells. For this IonFlux HT plate, there are 32 patterns, and there will be 2 recordings produced in each experimental pattern. An experimental pattern consists of 12 interconnected wells. There are 2 recording regions, which we refer to as Trap 1 and Trap 2, T1 and T2. These are the equivalent of the patch pipette, and these wells will be filled with internal solution. There's an inlet where the cell suspension will be loaded, and there's an outlet into which the solutions will flow. The path from the inlet to the outlet constitutes the main flow channel, and solution is continuously flowing through the main flow channel for the duration of the experiment. There are compound wells where different compounds or different concentrations of a given compound can be loaded, C1 to C8. Solution only flows from these wells when they are pressurized. The compounds can be injected in any order that one desires. The recording electrodes are placed in the traps with the reference electrode in the cell inlet, meaning that the electrodes will never see the compounds, so there's no concern about carryover between experimental runs. Given that the solutions are loaded into the plate prior to initiation of the experiment, there is no need for robotic liquid handling within the instrument, making for a much simpler and more robust automated patch clamp system. There are 2 versions of the plate available. To get your bearings on this slide, shown in red is a close-up of the region where the traps meet the main flow channel from the previous slide. The inverted L shape is the main flow channel. The inlet would be in the upper right, the traps below, and the outlet off to the left. The 8 lines coming into the main flow channel are the inlet lines from the C1 to C8. The initial design of the IonFlux plate was the ensemble recording version, which is shown on the left, where 20 cells are patched in parallel and a single recording is made. In essence, we are treating the ensemble like one very large cell. Shown on the right is our newer single cell configuration. In choosing between which configuration will be used for an experiment, the only difference is the plate type. The instrument can record from either an ensemble or single cell plate. So we have either 20 cells per recording with an ensemble plate or 1 cell per recording with a single cell plate. The seal resistances in the ensemble configuration for an average cell appear to be lower even though the single cell and ensemble plate are made from the same polymer. I will go into this in greater detail in a few slides, but the reason for this is that the ensemble is comprised of 20 different cells, and the lower resistance cells draws this average down. We do achieve gigaseal levels with the single cell configuration, but just as with manual patching, not every cell achieves gigaseal. For an IonFlux 16, there are 16 recordings per plate, and for the IonFlux HT, there are 64 recordings. In each case, up to 8 compounds can be tested per experimental pattern, which could be 64 unique compounds on the IonFlux 16 or 256 unique compounds on an IonFlux HT. The software interface has been designed to be as streamlined as the IonFlux itself. Upon opening the application, there are 3 tabs across the top: Setup, Runtime, and Data Analysis. On each tab are the context-sensitive selection buttons. Shown is the first page of the Setup tab, where one would enter the notation for the experimental run, such as the compounds within the wells. The second page within the Setup tab is where one would define the experimental sequence. For instance, if we were to run an experiment on an IonFlux HT where we wanted to compare two compounds against two different NAV channels, NAV 1.7 and NAV 1.8, we may set up the plate in the following way. In zones 1 and 2, we will use NAV 1.7 cells, and then in zones 3 and 4, NAV 1.8 cells. Each zone will have 8 patterns, with each pattern giving 2 recordings. So we have 32 NAV 1.7 recordings and 32 NAV 1.8 recordings. A few of the patterns will serve as negative controls. So within the compound wells, there will be only clean extracellular solution, or ECS. In the treatment groups, the cells will first see ECS from the C1 well, then escalating concentrations of compounds, in this case either lidocaine or another NAV blocker, A803-467. And then the final pulse of ECS will come from the C8 well. With our notes in place, we are ready to proceed with defining the experimental sequence. Due to the time, I will skip the priming, patching, and breaking phases, which will take up the first 3 minutes of the run, and skip to the data acquisition phase, where we have our compound addition editor and voltage command editor. In this example, the compound addition sequence is fairly simple. After the first 4 minutes, where only the main channel is flowing, the compound from the C1 position, which in this case is simply buffer, will flow into the main flow channel and stream over the cells for 2 minutes. This will happen in all 32 experimental patterns at exactly the same time. As soon as the C1 application stops, the C2 application for 2 minutes begins. The C2 application will vary across the plate. It will be either the low concentration of lidocaine or the low concentration of A803-467, or, for the negative controls, the only buffer. In a similar fashion, the C3 to C7 applications will occur, each lasting for 2 minutes. And then finally, the C8 application, which in this case is once again only buffer, will last for a minute. The entire experiment will take about 20 minutes to run. And once every 10 seconds, a voltage pulse will be run. This is defined in the voltage command editor. Shown is a test where the cells are being held at -65. Then there's a brief step to -120, then a step to 0 millivolts to evoke the sodium current, with a recovery at -120 before returning to our holding potential. Changing the voltage command is easy with our drag and drop voltage command editor. Within the voltage command editor, there are a selection of event types. To add a new event type to the sequence, one simply selects the event type and places it within the sequence. Then, when one clicks on the event within the sequence, the parameter window below the sequence shows the variables for the event, such as the baseline value, baseline duration, pulse value, and pulse duration, and the number of repetitions of the pulse. In the timeline chart, the event being edited is highlighted in red. In this case, the small hyperpolarizing test pulse that we are running to evaluate the membrane resistance is highlighted. As well, we can set real-time cursors, which will be monitored as the experiment progresses. Returning for a moment to the issue raised on slide 7, comparing the single cell and ensemble measurements of seal resistance. What we are measuring with our small hyperpolarizing pulse is the total membrane resistance. For the ensemble, this measured resistance is reciprocal of the individual resistances in parallel, R1 to R20. Since we have a single measurement, we won't ever know the individual values, but we can refer to the average resistance of cells in the ensemble, here noted as R ensemble. Since the single plates are made of the same polymer, using values from real experiments, we can see how the ensemble resistance is affected. Shown in the lower right with the light blue bars are values from a single cell run with NAV 1.8. In this example, 90% of the cells were very tight with total membrane resistance near 1.5 gigaohm. The one somewhat leaky cell, cell number 3, was only at about 300 megaohm. If this were an ensemble then, the average cell in the ensemble would still be at about 1.3 gigaohm. Shown on the right is the case where we have more diversity in the population. Half of these cells are greater than a gigaohm, but the other half are less, with the worst one in the lot, cell number 3, at only around 20 megaohm. Perhaps not even a cell, but rather some debris. Having done a considerable amount of automated patching with different platforms, this type of distribution isn't particularly uncommon for some cell types. What we see in the dark blue is that if this were an ensemble, the average resistance would be low, around 90 megaohm. Shown on this slide is a comparison of resistances for single cell plates in orange and the equivalent resistance for ensemble plates in blue. This is for a set of NAV 1.8 experiments that were done using the same cells. What we see is that for the single cell plates is that greater than 80% of the cells in the single cell configuration have membrane resistances of 1 gigaohm or greater. By comparison, less than 20% of the ensemble recordings have an equivalent membrane resistance greater than a gigaohm. So we can conclude that even though we have a high percentage of gigaohm seals, in the ensemble configuration we will still have mostly sub-gigaseal levels. Now if we turn for a moment to look at the measured currents, shown here for illustration are currents from a different cell type. In this case it is an ASIC cell line, showing a frequency histogram of current amplitude for single cell experiments compared to the ensemble, single cell equivalent current. In the ensemble configuration, there is a much tighter distribution and 0 non-responders, whereas for the single cell experiment, there were few non-responders and a wider distribution of amplitudes. This overall tighter distribution of amplitudes and more recordings showing a response makes the ensemble mode of recording better suited for higher throughput levels. In the same vein, shown are NAV 1.8 currents generated on an IonFlux 16 using either a single cell plate, shown on the left, or an ensemble plate, shown on the right. These are overlays of all 16 recordings at a particular time in the experiment. For the single cell recordings, there were 70% of the cells at the gigaseal level with a fairly broad distribution of current amplitudes, with the one dark blue cell not showing any discernible current. On the right, with the ensemble, we have about 20% of the recordings with an equivalent resistance greater than a gigaohm. More importantly, we have all 16 recordings showing a nice response. There is some baseline jumping in the leakier recordings, but all are showing nice discernible currents. So with our single cell plate patching on our polymer, we do get gigaohm seal levels. Shown are membrane resistance values measured at 10 minutes into an experiment for an IonFlux HT run, and shown on the right is a frequency histogram. The seals hold up for the 20 minutes of the experiment. Shown are average values from a set of experiments done on the IonFlux 16 on the right, or experiments run on an IonFlux HT, on the right, the IonFlux 16 on the left, showing the measurements at different times through the experiment up to 20 minutes. For NAV 1.8, the current amplitudes from single cells are rather small. So using a cutoff at 100 picoamps, we're seeing greater than 60% of the recordings are at a usable, and again, the currents hold up for the duration of the experimental run. For NAV 1.7, we have a modestly lower level of gigaseal success. However, the current amplitudes tend to be much larger, so we can use a threshold level of 300 picoamps for amplitude. So overall, we have a pretty good success rate with NAV 1.7 in our single cell configuration. Turning to biophysical characterization of the NAVs on the IonFlux. For the rest of the presentation, I will be mixing single cell and ensemble recordings, with most of the data being in the ensemble configuration, as this was our first plate type. Shown on this slide is an activation current voltage plot done with a single cell plate. Shown on the left are sweep overlays for a representative cell generated from steps from -100 to +70 millivolts in 10 millivolt increments using a holding voltage of -120. Shown on the right is the average IV plot, where the currents from all the cells that pass threshold criteria were first normalized to peak. And this agrees well with expectations from manual patch for this channel. Here we are looking at one of the mutations that I noted in the introduction. The serine to threonine mutation at position 241 in human NAV 1.7 leads to a painful syndrome referred to as erythromalgia. This is a gain of function mutation due to shifts in activation and inactivation properties. Shown on the right are current voltage plots for the wild type, shown in blue, and the S241T mutant, shown in red. This data was collected in the ensemble mode on an IonFlux 16 at the Waxman lab at Yale. Shown in the upper left are the time series plots collected as the experiment was running. Half the plate, the patterns 1 to 8, were with wild type, and the other half of the plate was with the mutant. So in real time, we were clearly seeing this difference in gating properties between these two mutants. And note also for the wild type trace that this agrees well with what we're seeing from the single cell plate. And the data also agrees well with the manual patch data that was reported for these mutants in the group's 2006 JBC article noted down in the lower left. Looking at the activation of a different NAV, NAV 1.3, again done in the ensemble mode on an IonFlux 16. In this particular experiment, two variants were being compared. While there's a slight difference in current amplitude, we don't see any difference in the activation kinetics. In contrast, looking at the steady state inactivation, we do see a difference in the inactivation properties. In this experiment, cells are held at -90 and then stepped for half a second to varied values from -180 to -20, followed by an activating step to 20 millivolts. The last type of biophysical characterization that I wanted to show was a recovery from inactivation experiment done with NAV 1.7 in the ensemble mode. This is a two-pulse experiment where the time between the end of the first pulse and the beginning of the second pulse is varied to see how long it takes for the current to fully recover. I like this particular experiment because it reinforces the point from the previous slide that meaningful biophysical characterization can be done in the ensemble mode. Here, the NAV 1.7 current is very large, around 35 nanoamps, due to the ensemble condition. Nonetheless, the response agrees well with expectations for this channel. Turning now to pharmacological characterization. In this experiment, with NAV 1.8, we're using a use-dependent test protocol shown in the inset. The cells are being held at -100 millivolts and then stepped to -10 millivolts for 20 milliseconds to evoke current. There are a set of 8 such pulses and then a prolonged period at a partially inactivated level before a final 9th pulse to 10 millivolts. Compounds that show use dependence, like lidocaine used in this example, show an increase in potency at the 8th and 9th pulse. Plotted are the measurements of the NAV current remaining for the first test pulse, shown in red, and the 8th shown in green, and the 9th shown in blue. On the right are the concentration response curves generated from these different measurements, showing the distinct increase in potency at the 8th and 9th test pulses. And then at the bottom are summarized the IC50 calculations. Here is a similar experiment done using tetracaine and NAV 1.7. Once again, we are clearly seeing the use-dependent block by lidocaine, shown in both the measurements from the test pulses plotted over time, as well as the concentration response curves with the distinct leftward shift with the use-dependent, the 8th and 9th test pulses. And again, the summary showing the increase in potency in the lower table. A803467 is a compound developed in collaboration between Icogen and Abbott Labs. This compound shows selectivity for NAV 1.8. Shown is a time series plot of peak currents. In this experiment, two different concentration ranges were tested. Shown in the upper panel is one ensemble, the light green trace, that was exposed to an escalating concentration series from 3 nanomolar to 1 micromolar. The gray trace is a negative control ensemble. In the lower panel is a shorter experiment where the range tested was from 30 nanomolar to 1 micromolar. The concentration response curves are shown on the right with calculated IC50s of 118 and 150 nanomolar respectively. Shown here are sweep overlays for ensembles in the previous slide. The first panel in green corresponds to the green trace from the previous slide, showing the reduction in current amplitude with increasing concentrations of A803467. And again, looking at the current amplitudes, we can tell this was done in the ensemble mode. The middle panel is the negative control ensemble, showing little change in amplitude of current during the time course of the experiment. And the final panel is the shorter, higher concentration test series. Similar experiments with NAV 1.7 clearly demonstrate that the compound is less potent. Note here that we're using a much higher concentration range, going from 0.3 up to 100 micromolar. And shown are two different ensembles, as well as a negative control ensemble. And if anything, we're seeing a bit of rundown, which in this case would tend to overestimate the inhibition. And nonetheless, there's an order of magnitude difference in potency between the NAV 1.8 and NAV 1.7 subtypes. In summary, the IonFlux platform is ideal for characterization of NAVs. Ensemble and gigaseal recording configurations allow for detailed characterization and increased productivity. The intuitive user interface and execution across the entire plate reduce setup and running times. And both biophysical properties and pharmacological characterization show good correspondence with the expectations from manual patch data. The IonFlux key advantages are flexibility. We have both gigaseal recordings, which provide detailed single-cell data, and the ensemble recordings for higher success rate. We have continuous perfusion and synchronous operation. The true continuous perfusion solves a number of challenges and shortens experimental time. And lastly, although not noted in this presentation, the system is capable of doing experiments at physiological temperature. I'd like to thank you for taking the time today to join our webinar.